Okay, so I'm going to talk to you about my main research interest, which is ultra-fast transient absorption spectroscopy, which means using femtosecond light pulses to study the transient properties of matter. So I will start with an introduction, a very general introduction to ultra-fast spectroscopy. Then I will give you the basics of the most common ultra-fast technique, which is PAM-probe, or transient absorption. I will try to explain this technique, how it works, and what information it gives, and how it can be implemented practically. And then, if I have time, I would like to give some examples of applications of this technique to study problems related to the photophysics of molecules, biomolecules, and so to show the power of the technique. So let's start with the introduction to ultra-fast spectroscopy. So essentially what you want to do is you want to use very short flashes of light to capture phenomena that are too fast to be observed by our eye. And if we want to give an historical perspective on this topic, we can start from this painting from the mid-19th century, which is called Le Derby des Psaumes. This is made by the French painter Théodore Géricault. And this is showing some galloping horses. And this is the galloping motion of the horse is too fast to be resolved by our eye. So this is how the painter imagined that the galloping phase, when all the four hooves are lifted from the ground, would be with the four legs spread apart. Now, is it really the way the horse gallops? To answer this question, you need to make an experiment, an ultra-fast experiment. You need to use short flashes of light to freeze the motion of the horse. And actually, historically, the first experiment was done by this gentleman, Edward Muybridge, who was a photographer, who was sponsored by Leland Stanford, who, besides being the founder of Stanford University, was also one of the richest men of the United States, having built a railway across the States. So Stanford gave to Muybridge the task to develop a flash photography with a resolution of 1 millisecond. And this very famous set of photographs was shot on the Palo Alto racetrack in 1878, showing with a millisecond time resolution the different phases of galloping of the horse. And indeed, you can see that when the four hooves are lifted from the ground, the legs are not spread apart, but they're rather close together. So the way the horse gallops is completely different from the imagination of the painter in the 19th century. So indeed, he could, if you put together these images, you make really a slow motion movement, a slow motion movie of the galloping phase. You can do it with many different animals. So here you have a time resolution on the order of 1 millisecond. And indeed now, if you go to a 20th century painting of a galloping horse, now the picture is correct, thanks to the information that we have learned. Now, the question is, how fast can you make the flashes of light? How fast can you look at phenomena? So another milestone was established by Harold Edgerton at MIT, who developed stroboscopic photography in the 1940s, that have a resolution on the order of a microsecond. So you go down 3 orders of magnitude, from millisecond to microsecond. Now, the question is, what kind of resolution would you need if you would like to make a movie of a molecule, of the dynamics of a molecule? And to understand this, you can make a very simple argument that was made by Ahmed Zewail during his Nobel Prize lecture for a Nobel Prize for femtochemistry. So the argument by Zewail is, if you look at atoms within molecules, they move with an approximate speed of 10 to the 3 meters per second. And the interatomic distances in a molecule are on the order of an angstrom, so 10 to the minus 10 meters. So if you want to detect atoms moving over such length with such a speed, it's very easy to calculate. You divide d by v, and you get a time resolution of 10 to the minus 13 seconds. So on the order of 100 femtoseconds. So you see that in order to observe the dynamics of atoms within molecules, you need femtosecond pulses. And indeed, if you look at photoinduced processes in molecules, you find that they happen over a wide range of time scales, ranging from few femtoseconds for electronic dephasing, energy transfer, solvent relaxation, and charge transfer, all the way to longer time scales, to nanoseconds, or even longer time scales. So there is a wide variety of molecular processes that occur on ultra-fast time scales. The same is true if you look at solid-state materials, for example, semiconductors. You have a lot of processes such as Wenger polymerization, carrier scattering, carrier phonons scattering, and so on, that occur over a variety of time scales from a few femtoseconds all the way to microseconds and longer. So you want to be able to study these processes with very short flashes of light. Now, the question is, how do you make these short flashes of light? Now, to put this into a perspective, how short are these pulses that you need to generate? If you consider now the heartbeat, which is about 1 second, if you go now to long times, the human lifetime is 10 to the 9 seconds, and the age of the universe is 10 to the 17 seconds approximately. Now, if you go to short time scales, you see that the molecular motion, maybe we start with the clock of the computer. The computer typically works at gigahertz. So the clock of the computer is 1 nanosecond, 10 to the minus 9 seconds. If you look at the motion of molecules, this is between picoseconds and femtoseconds. If you really want to go inside the atoms and look at the motion of electrons within atoms, for example, the orbital period of the famous Bohr atom of the hydrogen, of the electron and hydrogen atom, is on the order of 10 to the minus 18 seconds. So you go even to the attosecond scale. Now, the question is, how do you access this extremely short time? And of course, to do this, you need the laser. Now, before the invention of the laser in 1960, the shortest possible man-made event was the so-called Kerr shutter at a duration of 10 nanoseconds. So you could generate pulses of light on the order of tens of nanoseconds, and you could use them to study fast processes. And indeed, a lot of interesting things were studied with this resolution. The so-called flash photolysis gave to Norrish and Porter the Nobel Prize in Chemistry in 1967. However, after the invention of the laser, approximately the laser was invented in 1960, already in 1965, the technique of mode locking was invented, and it was possible to generate light pulses of the duration of 10 picoseconds. So again, it was a dramatic decrease by 3 orders of magnitude. And then there was a rush to generate shorter and shorter pulses, breaking the picosecond barrier with dye lasers. And in 1988, there was a milestone result where pulses of 6 femtoseconds in the visible were generated. Then the technology changed, solid-state lasers were adopted, in particular titanium sapphire, and again, pulses on the order of maybe 4 or 5 femtoseconds were achieved. Now, this is what can be done in the visible. Of course, if you now move to shorter wavelength, the XUV, you enter into the attosecond regime, but I will not discuss this in this talk. So you can essentially make pulses of a few femtoseconds in the visible. Now, you may ask yourself why there was this very quick progress, and then in the visible now we are more or less stuck since 30 years or even more, 40 years at a few femtoseconds. Well, the reason is very simple. If you consider that the limit in a pulse duration is the optical cycle. So if you consider a light pulse as an oscillating electromagnetic wave, this is now the electric field of light oscillates with a period, and the period is given by the wavelength divided by the speed of light. So if you take, for simplicity, a red light with a wavelength of 600 nanometer, the period, if you divide 600 nanometer by the speed of light, you get 2 femtoseconds. So 2 femtoseconds is the oscillating period of visible light. So these pulses are called the few optical cycle pulses because they contain just a few periods, maybe 2, 3 periods of oscillation of the electromagnetic, of the so-called carrier wave of light. So they are approaching the ultimate limit, which would be a single cycle of oscillation. So that's why we are in the visible, at least, more or less at the limit. Of course, if you now go to shorter wavelengths, if you go to the X-rays, then the period becomes much shorter, and you can indeed generate and exploit attosecond pulses. Now, in fact, the current record in the XUV is 50 attoseconds, but this would be a different lecture. I will not discuss it. Now, how can you use these pulses to make movies of photoinduced processes? The most common technique is a pan-probe spectroscopy. So I will give now a general introduction to what the technique does and how it is practically implemented. Now, if you consider these experiments, in general, these are a third-order nonlinear optical experiment, meaning that you look at a third-order nonlinear optical response. So in principle, in these experiments, the system interacts with a sequence of 3 separate pulses. This is in the most general cases, pulse 1, pulse 2, and pulse 3. Now, pulse 1 perturbs the sample and creates a coherent polarization. Now, pulse 2, after a given time, which is called the coherence time, interacts again with the sample and changes the population. And then after a second time, which is called the population time or waiting time, the third pulse interacts again with the sample, and it creates a third-order polarization, which is a function of these 2 times, the coherence time, the waiting time, and the third time, which is known as the detection time. So this is the most general third-order time-resolved optical experiment. And indeed, in some implementations, we have 3 separate pulses, but I won't discuss this today. Now, the most simple way is to merge pulses 1 and 2, and then we have the so-called pan-probe spectroscopy. So in pan-probe spectroscopy, this coherence time is set to 0. So you have 2 interactions with the pump pulse, which already perturbs the population in the sample, so creates an excited state population in the sample. Then, with the probe, you have a third interaction, which generates now a third-order polarization, which you can see here, this red field oscillating. Now, this, of course, is a function of the delay between the 2 pump pulses, which is 0, the waiting time t, and the detection time small t. So now this polarization will emit a field, and the field is emitted in the same direction of the probe. So what you are detecting is the superposition of the probe field with the field emitted by this third-order polarization. So this is what is called an optical heterodyning, because you are detecting your nonlinear signal superimposed with the probe, and this is called self-heterodyned configuration. So this is the theoretical basis of pan-probe. How do you do it in practice? In practice, it is very simple. You take a sample, and this sample can be anything from a gas to a liquid to a solid sample. And you start with the first pulse, ultra-short pulse, which is the pump. Now, the pump resonantly excites the system. So it deposits some energy. It can excite an electronic transition. It can excite a vibrational transition of the system if you go to the infrared. But it triggers a dynamical process that then you want to follow with a time-delayed probe pulse. So now the time-delayed probe detects how the transmission of the pump changes. So you detect how the transmission of the probe changes as a function of the delay with respect to the pump. And here you have a detector. Now, notice that both pump and probe are very short. It can be a few femtoseconds, but the detector doesn't need to resolve the temporal structure of the pulse. It is a slow detector. It only measures the transmission. So it counts the number of photons transmitted. And what you measure is this differential transmission, which is the transmission of the sample in the presence of the pump, minus the transmission without pump, normalized by the transmission without pump. Now, this is how the experiment works in practice. You use a non-collinear configuration, so the pump and probe propagate along different directions at a small angle, so that you can easily, after the sample, select the probe with an iris and go to a detector. And so you get rid of the pump. Now, what signals can you observe in a pump probe experiment? Assuming that we have a basic two-level system with a ground and an excited electronic state. So we come with all our, say, molecules are in the ground state. So if we come with our pulse, pump pulse, we promote a fraction of these molecules from the ground to the electronic state. So we are depleting our ground state and we are populating our electronic state. Now, the first signal that we can observe is known as photobleaching. Since we have decreased the number of molecules in the ground state, the absorption of the sample is decreased. So we are bleaching, we are making the sample more transparent in the sense that we are decreasing the ground state absorption. And so the transmission increases. We have a positive differential transmission. A second signal that we can observe is a stimulated emission. Now, we have populated our excited state, and with our probe, we can stimulate an emission from the excited state to, for example, a vibrational transition of the ground state or another electronic state. So what is the difference? Again, here we have an increase in transmission, so we have a positive differential transmission signal. But now we are really amplifying our probe. So instead of reducing its absorption, as in the photobleaching, now we have a real optical gain. We have an optical amplification of our probe. And the third kind of signal is known as photoinduced absorption. And this goes from the excited state to higher line states. And this results in a decreased so now, since you have populated this state, you can enable absorption to the state. So in this case, you have an increased absorption, so a decreased transmission. So the differential transmission is a negative sign. So these are the basic signals that you can observe and that I will show you in my examples. Now, what is the temporal resolution of pump probe? The temporal resolution of pump probe depends essentially on the duration of the pump and the probe. So you can express it as the convolution of the sample response function with the so-called instrumental response function, which is the cross correlation between pump and probe intensity temporal profiles. This means that if you want to increase the temporal resolution of your experiment, you need to use very short pump and probe pulses. So you need to decrease the duration of your pump and probe pulses. And in principle, as I will show you in my example, you can generate pump and probe pulses which have a duration on the order of 10 femtoseconds or even shorter. So you can do a pump probe spectroscopy with really high time resolution. Now, what is the simplest setup that you can use? So it's the so-called degenerate setup. So you take a single ultra-short pulse and you split it with a beam splitter into two identical replicas. One acts as the pump and the second acts as the probe. Now, typically the probe is attenuated because you want the probe to be just perturbative, to probe the variation of transmission. So it needs to be much weaker than the pump, but this is easily done with an optical filter that reduces the intensity. And you can control the delay between pump and probe with a mechanical delay line. And you focus with a lens or with a mirror both pumps on the sample. After the sample, you select only the probe with an iris, and you send it to a photodetector where you have then which is coupled to a lock-in amplifier. I will explain the lock-in amplifier in a moment. So essentially, here you see that the time resolution is given by the duration of this pulse. So if you have a short pulse on the order of 10 femtosecond, you can easily have a time resolution of 10 femtosecond. And this delay can be controlled with a very high precision of a few femtoseconds. And now, what is the sensitivity? What is the minimum signal, the minimum variation of transmission that you can measure? Of course, you need to average over multiple pair of pump and probe pulses. And so the sensitivity typically depends on the repetition rate of your laser. So how many pulses per second are illuminating your sample. So if you use a kilohertz laser, so with 1,000 pulses per second, which is typically an amplified laser, typically you have a sensitivity of maybe 10 to the minus 4. So this is what you can typically measure. But if you now go to higher repetition rate, up to 100 megahertz, you can go down to 10 to the minus 7. So you can really detect very small signals. This technique can be very sensitive. So here I mentioned the lock-in amplifier. Now, what does the lock-in detection do? Essentially, what you are doing, you want to compare the signal in the presence and the absence of the pump. So what you do is you typically you modulate on and off your pump, and you see that when the pump, for example, is present, in this case, the probe transmission is increased, in this example. When the pump is shut off, the probe transmission is the usual. So what we want to detect is this variation of the probe intensity in the presence of the pump. And actually, the lock-in amplifier does precisely this. It detects the variation of the probe by automatically subtracting the probe intensity in the absence of the pump pulse. So the lock-in detector, it detects this small variation of the probe intensity caused by the pump. So that's why it is typically used. Now, this is what I've shown you is the simplest way to do pump probe, but of course it's limited because you can only probe at the same frequency, at the same wavelength at which you excite your pump. Now, another way to do it is to do a broadband pump probe. So in this case, what you do is you start from a laser, you generate a tunable pulse by an optical parametric amplifier, which I will explain in a moment. Then also using another phenomenon, which I will discuss, which is called white light generation, you generate a broadband probe. Now the probe is not now, contains many colors, many frequencies. Then you combine pump and probe on the sample. And after the sample, you detect the probe on a so-called optical multi-channel analyzer, which is a spectrometer. So essentially, you measure the spectrum of the probe. So you don't measure the probe at a single wavelength, but you measure the full spectrum of the probe. And this is typically done by white light continuum in a bulk material. Now, the optical parametric amplifier, which is a critical device for making for generating tunable pulses, is I like to call it a photon cutter. So it exploits a second order nonlinear process whereby a high energy photon, the pump, is absorbed to a virtual level. You have a signal pulse photon that is amplified, and you generate because of conservation of energy, a third photon, which is called the idler, which is exactly the difference between the pump and the signal frequencies. So you can consider this as cutting the pump photon into the sum of a signal and an hydrogen photon. And since you can do this cut in many different ways, this is intrinsically a broadband amplifier. So you can use this optical parametric amplifier to generate your pulses, your pump pulses at any frequency. And this is very useful because if you want to study many different materials, you need to be able to select your pump wavelength in resonance with the absorption of the molecule of the material that you want to study. So it is crucial to have a tunable pump, and this is done with the so-called optical parametric amplifier. Now, you can do a very broad tunability with this, and now what you can do is you can do to generate a broadband probe pulse, you can use the phenomenon known as femtosecond white light generation. So what you do, this phenomenon exploits a third-order nonlinear process, which is called the self-phase modulation. So essentially, when the intensity of your beam is high enough, the refractive index of the material becomes a function of the intensity. So this means that as the intensity of a pulse changes in time, you will have a phase shift introduced on your material, which changes in time. And also you will have a frequency shift, also time dependent. So during, if you illuminate this material with a short pulse, your instantaneous frequency will shift first to the red, because when you are on this rising edge of the pulse, and then to the blue when you are on the trailing edge. So this is a rather spectacular effect. Here I'm showing you an infrared pulse, which is focused on just a piece of glass. This is essentially just a piece of transparent material. And you see at the output a white light. Now, white light contains all the colors of visible. In fact, here you see a grating, and you see all colors from the red to the blue. So this is a very useful technique because now you have all the colors contained in this white light that you can use as a probe. So you can interrogate the sample, not just at one frequency, but over a very broad range of frequencies. And indeed, here I'm showing you that with the white light, you can really make broadband white light using different materials that go from the ultraviolet all the way to the infrared. So you can really interrogate, okay, I'm going to skip a couple of slides, interrogate a wide range of transitions. Now, another thing that I want to mention is that using this optical parametric amplifier, you can really also make very short pulses. Now, if you use the so-called non-collinear OPA, the non-collinear interaction guarantees a broadband amplification of a white light continuum, and using the so-called non-collinear OPA, you can generate really short pulses. And in fact, here I'm showing you some of the pulses that we generate in our labs using these non-collinear OPAs, which have a duration less than 10 femtoseconds. This is, for example, a pulse in the visible with a duration of 5 femtoseconds. And all the way you can go to the infrared and also to the ultraviolet, maintaining these really short pulses. So this is also very useful if you want to look at phenomena that occur over very short time scales. Now, let me show you a typical measurement. So what you do if you have a broadband probe, you will measure a map of differential transmission as a function of the probe wavelength and of the probe delay. And this is a two-dimensional matrix where you have for every wavelength and for every delay a value of the signal. Now, what you can do is you can take, for example, a cut at a given wavelength, and then you get the dynamics at this specific wavelength, or you get a cut at a given delay, and you get the differential transmission spectrum. So these are the typical maps that you can acquire. Now, in the remaining maybe 15 minutes, I hope I can show you some examples of applications. So I will start with the case of materials for organic photovoltaics, where you want to make a plastic solar cell. So you typically mix a conjugated polymer, in this case PPV, with an electron acceptor, which in this case is C60 or fullerene. So if you make this blend, what you do is that the polymer is absorbing the visible light, and it creates within, let's say, the polymer, you have an electron hole pair, which is an exciton, but then the electron very quickly jumps to the fullerene, and then you have a charge separation. There is an ultra-fast electron transfer from the fullerene, and then the charges can percolate to the electrodes, and you get a photocurrent. So essentially, you are getting charge separation, and you get a photovoltaic cell. And this can be, with respect to silicon, it has the potential to be much cheaper and easier to produce. It's a plastic cell that can be bent. So there is a lot of interest in studying this fundamental process of charge separation in this material. So this is an experiment that we did some time ago, looking at, in this prototypical blend, at how long it takes for the electron to jump from the polymer to the fullerene. Now, here is one of these maps that I was explaining. Here is the wavelength. Here we are probing in the visible. And here is the time delay from -100 to 300 femtoseconds. So we really focus on the very early times. And here the time resolution is 10 femtoseconds. So of course, here you have your time zero. Now I'm taking here a cut, for example, at 620 nanometer. So I see, first of all, a positive signal. Now this positive signal is the stimulated emission from the polymer. So I am exciting my polymer, and I'm getting a stimulated emission, meaning that I've created this exciton, this electron hole pair within the polymer. But then very rapidly, the signal decays, and it becomes a negative signal, a photoinduced absorption. This is known as the photoinduced absorption of a charged polymer, so PPV+. This is a so-called polaron. So we see that this signal is formed in about 200 femtoseconds. So after 200 femtoseconds, the stimulated emission has disappeared, the polaron, the charged state has been formed. This means that the electron has jumped from the polymer to the fullerene with a time constant of 55 femtoseconds. So we can really characterize with this technique how long it takes to jump from the polymer to the fullerene. So the fundamental process that underlies charges the photovoltaic operation of this device. Of course, this is a prototypical experiment. We have done experiments on many different blends, even much more sophisticated. A second example I want to give is excited state dynamics of carotenoids. Now, carotenoids are among the most widespread natural pigments, giving colors to many plants and fluids, and they belong to the family of polyenes, which are linear chains of conjugated carbon atoms joined by alternating single and double bonds. So here you have to think of carbon atoms, I'm not representing them, and you have this conjugation. Now, carotenoids are present in all plants, and they play a key role. They essentially, without carotenoids, all plants would die. So they are very important molecules. Now, if you look at the excited state dynamics of carotenoids, it is quite interesting because the first optically allowed state, the so-called bright state, is not the lowest lying excited state, but it's the second. So this means that there is a optically forbidden state, a dark state, which lies in energy below the allowed state. So there is this dark state, and now this dark state acts as a sink for the energy. So there will be an extremely fast, once you excite the bright state, energy will flow to this dark state over a very fast time scale, on the order of, again, 2 to 500 femtoseconds. And then now this state is characterized by a very intense photoinduced absorption band in the visible. Now, I want to give you again an example. This is almost a textbook example of this process. I'm taking spheroidine, which is a carotenoid with 10 conjugated double bonds. You can count them here, which is found in several plants and algae. Now, here I'm taking just a carotenoid, and this is again a differential transmission as a function of time and, in this case, photon energy. And here I'm going from the visible all the way to the near infrared. So again, here I'm doing experiment with 10 femtosecond time resolution. So as I excite my molecule, first of all, I see a strong stimulated emission, which is from the bright state. And I see also a photoinduced absorption. Now, this photoinduced absorption is coming from again, from the bright state. But these two signals, you see, they disappear very quickly. After 200 femtoseconds, they are gone. And there is a new, very intense signal that is built up, which we call PA1. And this is known to be the photoinduced absorption of the dark state. So you see within 200 femtoseconds, the bright state disappears and the dark state is formed. So again, you are observing the basic step of bright to dark state conversion, which takes place with a time constant of approximately 150 femtoseconds. So again, thanks to our high time resolution, we can look at this process, which plays a key role in photosynthesis. Now, the very last and maybe fascinating example I want to give you is the ultrafast dynamics of the primary event of vision. So what happens within our retina when a photon strikes our retina? Now, if you look at retinal, there are so-called retinal proteins which are contained in our retina, which have this structure. They consist of 7 alpha helices, you see these ribbons, which contain a small chromophore, which is known as retinal, which is the only part of this big protein that absorbs light in the visible, because these are essentially amino acids that only absorb in the ultraviolet. Now, let me go to the eye. In the eye, you have your photoreceptors that are contained in the cones and the rods. And in all the cones and the rods, you have these opsin proteins. You will have the conopsins in the cones and the rhodopsins in the rod. Now, as I told you, the rhodopsin consists of this protein pocket. Here I'm showing you these 7 alpha helices as ribbons that contains the retinal, which is the only part of the protein that is sensitive to visible light. Now, what happens when a photon strikes rhodopsin? Here I'm showing you a cartoon where you see the ribbons as cylinders and you see the retinal here inside. Now, what happens is an ultra-fast process of, you see that the chromophore is in the so-called 11-cis configuration. So it is, and it is when a photon strikes the protein, you have this ultra-fast cis-trans isomerization. And now this provokes an expansion of the protein pocket, because now it needs to fit the new shape of the chromophore. And then you see that this cytoplasmic tail becomes uncoiled. Now, but the primary event of vision, the very first step, is this cis-trans isomerization of rhodopsin. Now, this is a complicated photocycle, but we really focus on this very primary event, which has a quantum yield and efficiency of 65%. So our eye is indeed a very sensitive detector because it has an efficiency of 65%, like the best maybe silicon photodetectors. Now, this was one of the first experiments that was performed when femtosecond laser were available. And it was demonstrated that this effect, this process is ultra fast. In fact, how was this demonstrated? If you go from the excited state of the 11-cis, you go to the ground state of the photoproduct, and you see this photoinduced absorption from the ground state, and which is quite intense. And this photoinduced absorption was observed in these seminal experiments to be formed in about 200 femtoseconds. So we know indeed that the isomerization is completed in 200 femtoseconds. So it's an extremely fast process. Now, if we wanted to look at in detail at this, you can consider the following scenario. So you have a wave packet in the excited state of the reactant of the 11 cis. You absorb a photon, you bring it up to the excited state again of the reactant of the 11 cis. Then the wave packet slides and it arrives to the all-trans photoproduct. So there is here a region where the two surfaces cross, and this region is called a conical intersection. And this is really a point where the two surfaces, they become degenerate and they cross. And so this is what promotes this very efficient decay, in this case, isomerization, so the conversion of photon energy into chemical energy. So we want to focus in detail, want to follow in detail what happens when the wave packet moves to the conical intersection and eventually reaches it. Now, what I was saying are these very important, these are very general features in photochemistry. They are collections of molecular geometry in which two or more states become isoenergetic. And so they are doorways for a molecule to relax to another electronic state. Now, okay, so how can you think of following the rhodopsin atomization in real time? So you have your wave packet in the excited state. You expect to see a stimulated emission. But now you see that this gap between the two states is progressively decreasing. So the stimulated emission is shifting very rapidly to the red. Then the wave packet jumps through the conical intersection to the ground state. And in the ground state, now we don't have a stimulated emission, but we have a photoinduced absorption. And this photoinduced absorption very quickly shifts to the blue, because now this gap, you see, is progressively increasing. So the telltale signature of a wave packet moving through a conical intersection should be a stimulated emission shifting to the blue, to the red, sorry, followed by a photoinduced absorption very quickly shifting to the blue. So this is a difficult experiment because it requires very short pulses, because everything is completed in 200 femtoseconds, and it requires the ability to probe at different wavelengths. And indeed, this is what we have done, this experiment using very short pulses from the visible to the infrared. Now I will, since I'm running out of time, I will directly jump maybe to the result, which is this one here. So here I'm now putting together infrared and visible measurement. So this is again one of these maps that I was discussing. You have the wavelength and you have the time delay. And here you see the wave packet. And again, the color code, blue is stimulated emission, red is photoinduced absorption. So here we have a time resolution of 10 femtoseconds. So immediately after the pump, we see a wave packet that has a stimulated emission, you see blue, and this stimulated emission very quickly shifts to the red. After approximately 80 femtoseconds, this signal disappears because the wave packet now is moving to the conical intersection. We cannot observe it anymore. But then this signal reappears after 100 femtoseconds, but now the sign is changed. Now is a photoinduced absorption, and this photoinduced absorption very quickly shifts to the blue. So after 200 femtoseconds, everything is over. So the primary event of vision, this isomerization of rhodopsin, is indeed occurring through a conical intersection. We see the wave packet moving to the conical intersection and coming back. We cannot really observe the crossing of the conical intersection, and everything is completed in 200 femtoseconds. And indeed, we started a collaboration with a group of Marco Garavelli in Bologna, who did some very sophisticated numerical simulations, which reproduce very well our experimental results. So here you see the comparison of experimental results with numerical simulations, and of course the theory then gives you a lot of more information on really how the structure of this chromophore evolves over time. So you see the power of this technique to gain fundamental information on ultra-fast processes. Now, I have other examples, but I think I'm running out of time because we said we wanted to do about 45 minutes. So probably I would finish here and leave time for some questions if there are any. And with this, I would like, maybe let me quickly jump to my conclusion. I had also some results on DNA, but I don't have the time to present them. So in conclusion, transient absorption spectroscopy is a simple but powerful technique to study photo-induced dynamics. And in particular, you can use really short pulses that can be applied to really photograph primary photo-induced processes in biomolecules, such as the primary event of vision, which is isomerization of rhodopsin, and another example that I didn't do which is photoprotection mechanism in DNA. And with this, I would like to thank you for your attention.